And the next talk will be by Andriy Semenov here in Kyiv from Bogolyubov Institute. The title of the talk, Revealing Quantum Properties with Realistic Measurements. So Andriy, please take your place.
Thank you very much. Thank you very much for introducing me. Just technical things. So before technical things is starting, I would like to thank the organizer for inviting me this talk and for giving this impressive possibility to present results of our group for audience from 2 countries, actually. Yeah, please, just a moment. We must technically assist. And before I will start, we do with technical things. I will start my talk that I will talk about some, usually in quantum optics, in quantum technologies, in quantum studies in general, we are doing with some quantum phenomena like entanglement, like Bell non-locality, contextuality, optical non-classicality, which we call resources. And this is very important for us to sometimes to use these resources to identify these resources, and this is very impressive that all these phenomena, very different phenomena actually, can be considered from the unified point of view, so from the point of so-called resource theory. This is not what my talk about resource theory, but we use this resource theory because my talk, I will tell about some different phenomena, and this different phenomena can be unified with this resource theory. And important thing that if you have some resource, this is not only enough to you to have it. It's only important when this resource is properly analyzed. And sometimes your measurement devices, especially it happens in quantum optics, are not perfect, but you still want to see something. And in this talk, I will tell you how to maybe to take maximum from what we have in our real world situation, in real optical laboratory. Okay, just give me, let me have a couple of words about quantum resource theory. Quantum resource theory is not only about resource theory in general. This is not only about quantum resources. This is about a lot of different resources. And let us imagine some standard situation, some our everyday situation. Let's imagine that we wanted to prepare some, for example, open air events, some barbecue party, for example. Okay, in this case, like it happens on Friday, by the way, in Kyiv Academic University, maybe not with such weather, which we have now, but who knows. And in this case, for example, we have in our refrigerator some foods, and we can do everything from these foods. We have very easy operations so that we can use these foods, and we can prepare from these foods everything we want. In this case, these foods which are available for us very easy are called free states. And these operations which are easy for us, which do not require from us some additional efforts, are called free operations. But if you want to have something more, for example, a bottle of wine, and you don't want somewhat you do not have it here in your refrigerator, or I don't know, in your bar, so you have to do some additional resource, so some additional operations. So this is your resource bottle of wine, in this case your resource state, and you should go at least to a supermarket, not simply to open the refrigerator, and to buy it. So in this case, this is resource state and resource operation. Similarly work actually quantum physics, very similar way. For example, quantum entanglement. Free states in this case are all unentangled or so-called separable states. So this actually states which can be written like this with positive probabilities. I will not stop on this. But if you have your free operations, so if you only accessible operations for you are local operations, so when you do something locally on Alice and Bob sides, and classical communications, for example, you can call to each other with telephone, you have no chance to create entanglement. To create entanglement, you need something more, which calls resource. So entanglement, in this case, resource. Another resource is, for example, Bell non-locality. This is a bit different from, very similar to quantum entanglement, but a little bit different from this. And in my talk, I will focus also on another well-known resource, which is used also in quantum optics. This is optical non-classicality. Free states, in this case, are any quantum states that such states that when you provide some quantum measurement, you can always explain it with no need to quantize electromagnetic field. Actually, this is coherent states of the field, and any statistical mixture of such states. People from quantum optics know that this is states with positive definite Lauber-Sudarshan P function. Example, coherent states, thermal states, and so on. When you do free operations, so for example, free operations in this case, passive linear optics, this is simply some pieces of glasses, yeah, like beam splitters and so on. In the most general cases, it can also be beam splitter with some random transmission coefficient, for example, whatever you want. And you have no chance in this case to create something interesting like Fock state with a given number of photons, or squeeze states, or something like this. So in this case, your resources are non-classical quantum states. So quantum states which require quantum electrodynamics to describe them, to describe measurement results. Okay, what is a problem which I consider in my talk? When you make some measurement, so in quantum states do not exist alone. Always when you do when you operate in lab with quantum states, you need to make some quantum measurements, yeah? And for example, you have some quantum state of light. In principle, this can be whatever you want. And your measurement device converted in a value of some observable A. So this is some conversion. It's written like a Born rule. So this was in a previous talk also was mentioned. So you have quantum state, here you have statistic, and here you have very important characterization of measurement device, positive operator value measure, POVM, and actually this is what characterizes your device. It can be okay. You can do so. This is the point is that this information in this statistic, in principle, in many important situations, is not enough to reveal all information about your density operation, because it can be informationally incomplete. Okay. You can also do something more sophisticated. You can introduce some device setting. So maybe some switch on, switch off, some, I don't know, some switcher in order to change some setting device on device setting. And in this case, you have measurement statistics, not a single probability distribution, but probability distribution conditioning by settings, but still it can be informationally not complete. And the situation can be really interesting because, for example, you may have rho is your resource state. For example, rho is non-classical state, but statistics that you reconstruct can be free statistic. So, for example, this can be still reproduced with coherent states. Such situation is generally very possible, and this means that we cannot extract some non-classical properties or some resource property. So this resource is more or less useless for us. Yeah. Example with this metaphor with barbecue party. If this is your resource, bottle of wine is resource states, and all your measurement devices are restricted by this set, you do not have this corkscrew in this case, yeah? You do not have a chance to use it. So the result of your party without this device, without corkscrew, will be actually the same as without this bottle of wine. Yeah, okay. And what I would like to present you, so then in my talk, yeah. So the aim of my talk is twofold. So to present you some results. First of all, we want to show you about some theory for this positive operator measure for quantum optical experiments, for realistic quantum optical experiments, and to be more precise, I will talk about photo counting measurements. Photo counting measurements are important part of quantum optics, but the most terrible part of this photo counting experiments that in most realistic devices we cannot use normal. We cannot perfectly distinguish between the number of photons. Very often we can only say if we have if photon present in the electromagnetic field or not. And after that, we will to do everything possible in order to identify this non-classical resource or another resource with a given set of measurement device. Is it possible to do? So maybe like this in this picture. So maybe you do not need sometimes corkscrew, yeah, in order to understand how it works. Okay, let's start maybe first with this theory for realistic photon number measurements. And like I said, the most terrible situation in standard measurement devices, now we have much better measurement devices, okay, but standard situations that your measurement device cannot distinguish between number of photons. So this photo detector converts your electromagnetic mode of electromagnetic quantum state into some photo counts, but it does not tell you how many photons you have. It can tell you if you exist there or not. And maybe one of the nice proposals how to solve this problem is array of and of detector when you split your incident beams and in a number of another modes, temporal, so in this case spatial, but or temporal splitting can be. And in this paper by Jan Sperling, Werner Foger, and Girsh Agarwal in 2020, they have shown that this POVM has such a form, and this different actually from what we have in quantum optics in standard photo counting theory. Yeah, of course, this is what we should take into account. I will concentrate on a little bit different situation. And in this case, what happens, so a little bit different methodic of photo counting. When your photo detection is affected by dead and relaxation time, this is usually takes place for superconducting nanowire single photon detectors. And for many detectors also, but this is the most general situation from the theoretical point of view. So this superconducting detector, this nanowire detector, this is really a superconducting nanowire. It has temperature very close to critical, and here is current, which is also very close to critical. When photon is absorbed, you observe some pulse of voltage. And after that, this is slowly relaxating. And you can say that in some moment of time, you have measured, for example, some absorption photon. When you have two pulses in this moment of time, you have measured two photons. You may say that in this moment of time, that in this period of time, you had two photons. But there is a problem. The problem is that such detectors are not recovering very quickly. So there are small period of time, dead time. So then there is no chance for photon to detect after such pulse to detect photons. And after that, the detector is smoothly recovering. Yeah, so we should take it into account. So this smooth recovering is very nice described by time-dependent efficiency. This is black, this is dashed line here. And actually saying, so you have a very nice model for this, which works both analytically and experimentally. Yeah, so we can use it for our analytical analysis. Yeah, and actually we have derived for this case, very important case, sorry, I forgot about to say that after such an operation, we should darken our detector because it should not affect on another time window. Yeah, and after that, we have derived such a very nice formula for photo detection. It looks a little bit complicated, but nevertheless, it works. It can be used to analyze all our results. But I should say, so let's be honest, in experiment and real labs, nobody uses such luckiness of detectors. What happens if you have here, for example, no darkness, so when your next time window is follows after previous one without darkening mode? You can consider this situation. We have considered this situation. In this situation, you see what happens that in previous measurement time interval, you have effect on the next one and maybe from the very, very last time windows. And you have something like a memory effect. So your photo, oh, sorry, this Yaroslav does not work anymore. Yeah, okay, okay. Okay, thank you very much. You have already nonlinear dependence of statistics of photo counting on density operators. That is very, very interesting. So this is formula, this equation for this multi-photon POVM is just for information. I don't want to analyze it now. It's almost impossible maybe, but it's very easy, interesting to see that here you have some terms that, for example, you have effect not only from the current density operator, but first term in this Q chi is what happens with the last previous measurement window, with second but previous measurement window, and so on. So this is clearly memory effect, but it's not really surprising because in such situation you must have it. Okay, this is what I wanted to tell about our activity with this about this story with our realistic photo detection theory. And now I would like to go to how to apply it to identify some quantum resources, for example, non-classicality of photo counting statistics. In general, you have, again, this equation, and this equation convert you. So let's consider that you have probability distribution for registering n photo counts under conditions that your field amplitude is coherent for coherent states with some coherent amplitude alpha. So this is actually classical electromagnetic field. And you can write such equation, and people familiar with quantum optics told me, oh, okay, this red P from alpha, this is Glauber-Sudarshan function. But this is true, but not really true, because we can look at this equation as an integral equation for an unknown function P from alpha. And yes, there is one solution that is Glauber-Sudarshan P function, but another solution in this case, it can be when this measurement is not informationally complete. So you may have a lot of other solutions. And this means that you can reconstruct these statistics when among these solutions there are positive definite solution with classical electromagnetic field. So your field is totally quantum, but you still have something that can be classically interpreted. And in this case, to analyze these results, we can use the really results of which use in some resource theories. So in this case, we use something different because very close analogy to what people use in Bell inequality theory. And actually, we have such a theorem or such statement, which is actually nothing more as hyperplane, superting hyperplane theorem known in convex geometry. Yeah, and this says that if there exists positive definite solution for this equation, then for any function lambda from n, you can define its mean value E from lambda, its mean value for a classical field, and in this case, this inequality should satisfy. If you find such lambda that this inequality is violated, then your statistic is really non-classical, and this means that you cannot recover it with classical electromagnetic fields. But there is a problem because this is very difficult to consider all this. So this is, by the way, very easy to do with from quantum data and with classical data. So in experiment, this formula very easy to do. But the problem is that, oh, just a moment, that usually we cannot use this very difficult numerical problem to consider all possible all possible functions lambda from n. We should find some optimal set of this lambda of n. And in one hour paper, this way was proposed. Actually, this is very close to the idea in Bell inequalities, what people propose so-called facet or tight Bell inequalities. And the result is, for example, I will demonstrate with this photo counting. Yaroslav, it doesn't work again, sorry. Technical problems. And the result is for photo counting statistic, again, with this array of detector. And let's consider that this is only two, you have only two detectors. So your outcome is three events, zero clicks, 1 clicks, or 2 clicks. And so 2 clicks you may not consider because it depends on 0 click and 1 click. But in this case, what you have is that your probability distribution of classical electromagnetic field of coherent states in space of two probabilities is just a line, it's just a curve. And this is a convex curve. And all your classical fields are just something that is under this curve. And in the case of array detectors, but in the case of any other detectors also, you can derive some inequalities. You can combine, this will be linear inequalities, so-called. You can combine this in nonlinear. Very easy to find because this is everything that is under this curve. In this case, we have such inequality. We can generalize it for the case of n equals 3. In this case, situation is even a little bit more interesting because in the case of n equals 3, you have a line, a curve. And this curve is in the three-dimensional space. And you should consider convex set in three-dimensional set. Nevertheless, it's also possible to propose some inequalities for this case. And moreover, I can say that we can generalize this idea for at least for any odd number of detectors in the array. And this is just an example how it works for people. So this is so-called phase quiz coherent state. People in quantum optics know that usually we don't expect non-classicality of photo counting statistics for such states. I will not say why it happens, okay, because this is in phase direction, in another direction, this non-classical, and this direction, this non-classical. So this is something what we call the contour of Wigner function. And, but nevertheless, even for such things, states which are considered, for which non-classical statistic considers as highly classical, we can reveal non-classical properties. We understand that non-classical properties exist, and this is for some realistic situation, even with experimental, so with error bars, so exist. So this method really works, And okay, now I'm going to, I have still time, to another situation, to another resource, Bell non-locality. Actually, our study of optical non-classicality was, so we were impressed by Bell non-locality, where we were formulating these inequalities. So let's go back to Bell non-locality in order to understand what happens there. And the difference from this, in this case, from Bell non-locality, from the standard situation, maybe you know that in standard CHSH configuration, one usually considers so-called 2 times 2 configuration when you have, for example, Alice measure 2 observables and Bob measure 2 observables. Each of them has 2 values. In other cases, this is just optical scheme. I do not concentrate what means this optical scheme because this is so-called balanced homodyne detection and unbalanced homodyne detection. You have here some settings. You can make them discrete, these settings, also 2 settings. But in this case, at one side, you have, for example, discrete values, and in another way, you have continuous values. You can of course, write something that for generally, for like something like Bell inequalities, they're very similar to inequalities that I have shown you already. But this is not tight inequalities. This is not tight criteria. This is not, this is not tight criteria. This is not criteria. It is not really, it is not convenient to use. And people from Bell community may say, okay, when you have continuous, at least one continuous variable, it's really difficult to formulate these tight inequalities because it requires something from convex geometry in dimension with continuous variable. Our PhD student Vadim Kovtoniuk has found a very elegant solution, I see, for this problem, and we do formulate some inequalities. Idea was actually to present this lambda, that this also can depend on this function P. Actually, we consider very clear situation which people consider in the context of another similar task, but nevertheless with some interesting additional things. And alternative things, just to show you, not to analyze this equation again, can be written like this. So that's inequalities, yeah? And if they work, yes, they work, we can consider such state, which sometimes people consider as a hybrid entangled states or Schrödinger cat states or whatever you want. And yes, in this case, we see clear violation of Bell inequalities, even in such hybrid situation. I consider that this is nice because this is really necessary and sufficient solution condition, and this is optimal in principle set of such inequalities. Okay, I'm going to summary. My summary, what I have presented is photo counting theory with the time, relaxation time, and after pulses. Tight, we have presented time non-classicality criteria for realistic photo number resolution. We can revive reveal non-classical properties from such imperfect measurements. Tight non-locality criteria for hybrid measurement schemes. This is some of our last papers on this topic. And thank you very much for your attention. This is our group in Bogolyubov Institute, young people who do this impressive work, especially Vadim Kovtoniuk is here, whose results I was reported today also. And two other people are also here, Mikita and Ivan, Mikita Yeremenko and Mikita Klen and Ivan Yeremenko, sorry. Yes, they're also now here. Thank you very much. I'm ready to answer your questions.
Now it's time for questions, so please be active. So, okay, Larissa.
But microphone you can use.
Thank you very much, Andriy. Why these criteria are called tight?
Tight, okay, because it actually comes from the activity in Bell inequalities, yeah? More generally, in some convex geometry, in Bell inequalities, people also say facet inequalities. Yeah, tight means that in some condition means that, for example, you have in some space of this probability distributions. So this is something like a geometrical space. Yeah, you have some convex set, and this convex set is what your free states. In this sense, yeah, and your inequalities are just tangential hyperplanes, so-called supporting hyperplanes to these inequalities, yeah, to this surface, and they tightly bounded it. Okay. So this is why it's tight. Thank you.
So,
microphone,
please.
Alexey Vakhnenko, Bogolyubov Institute of Theoretical Physics. Here I thank you for a very interesting talk, but in quantum mechanics and in your theory of measurement, the process of measurement, is it possible to formalize the very process of measurement by strict theory? Because in quantum mechanics and in other theories, people talk about measurement, but the process of measurement, it's the black box, you see, and what have to do with this black box? Yeah?
Okay, thank you for your question. So I actually do not agree with you that this is totally black box, yeah? So this simply has some statements which are very fundamental statements about quantum state reduction, for example, yeah? But when we doing with quantum measurement theory, when we analyze realistic devices, We always deal with processes, with realistic equations which define our process. So this use, for example, this theory of quantum stochastic properties, which was reported in previous talks. Yeah, this is not easy problem, but yes, maybe you're right that there is some. There exists some additional axiomatic in quantum theory. This is not top secret. Yeah, that state reduction. So we should postulate it. Yeah, how to decide? Nobody knows how to describe it. It's a question, something like I consider philosophical. But to be honest, I'm not ready to discuss it today. Philosophical question. We can, of course, but
It's only words, because people say that, for example, the collapse of wave function. What it means? I never see any formal theory how this collapse take place. You see, it's only words and no more.
you see, this is not really true because you can see it in one standard situation, even in classical case, collapse of probabilities. For example, you have a coin, so you can consider hours of reverse of this coin. So you put in top, and this will be a totally classical process. This is not classical process, but before it's here on your table, this coin, for you, this is probability 50%
No.
that this will be here, and when it comes, probability is already determined. Yeah, so this is somehow analogy of this collapse. But we, of course, we do not have, when you consider wave function and when you want to describe your this process with some equation of this collapse of wave function, yeah, this is impossible to do. And actually, this is, yeah, okay.
It's only words.
Yeah, just with.
And my question is close to question of Alexei. You see, any process of measurement involves actually interaction between light and matter.
Yeah, of course.
Which is characterized by a fine structure constant alpha.
Okay, not so deep, but yes.
Yeah, but your probability depends.
Sure.
Suppose you take the same type of measurement in a place where alpha is another number.
How it's possible?
Yeah, people, for example,
in another universe?
Not only. For example, with changing energy.
Okay.
Alpha changes also.
So in some other,
you can make the conclusion about that from your measurements? Actually, maybe you say in this case that some process of measurement is another type which you consider.
You see, when you have, for example, so you mean that your process of measurement depends on some constant, on some parameter, and fundamental parameter, and you want to reconstruct the value of this fundamental parameter. To understand how it works.
Even
what you can consider in this case, because you can really model it with quantum, and this is actually things which are known, which people do in quantum metrology. So you can, for example, consider formally that you have some measurements results you will have some experiments. And after that, you have so-called hypothesis that your measurement or your density operator, for example, depends on this parameter, alpha or somewhere else. And you can apply statistical estimation theory in order to extract that value with some accuracy, of course. Yeah, even there is very big theory. This is quantum metrology, which gives you about limits for such accuracy and so on. But you will have for sure results of the measurements. But okay, you may not know the parameter. You may want to reconstruct it.
Maybe you make wrong wrong conclusion instead of dependence on fundamental parameter.
You may have
say
you-
that
you may have wrong zero hypothesis about dependence of your density operator on this parameter. This
Okay.
can be, this can be, this
Okay.
can be, this can be, yeah.
Okay. So, do you see anyone? Does anyone have questions online? I don't see.
No, there is no question.
No questions online.
No question.
So I don't see more questions in here. And so let's thank Andrei once more.
Thank you very much.